First of all, thanks to the organizers for the invitation. And apologies because probably this talk will look a little bit removed from what we have been listening to, but you should see the connection by the end. So essentially what I want to talk about is the quantum phase transition to the spin glass phase. So this work appeared on the archive just last week, and it's done in collaboration with my PhD student, Gianni Mossi, another student from the University of Milan, Tommaso Parolini, and postdoc at ICTP, Sebastiano Pilati. Okay, so let me tell you what I'm going to tell you, and in particular, what I want to insist on, which is a bit conjectural if you want, but I hope I will give you enough information, maybe not to convince you, but certainly to think about the problem. Okay, so I want to show you that there are indications of the fact that the quantum transition at zero temperature is inherently different from the transition at any finite temperature, which is in the end dominated by the classical point. The classical point will be the finite temperature transition, zero transverse field. And it has the phase transition is much better understood thinking in terms of the deep how the deep paramagnetic phase dies rather than how the deep spin glass phase gets dressed with the transverse field. Okay. In order to do this, we did a lot of numerics. In particular, we studied entanglement entropy with quantum Montecarlo, which was a challenge by itself, as you can imagine. And then we studied the more typical things like order parameter, spin-spin correlation functions, and we looked at the scaling. And the main motivation, the main argument that I said I want to make is given essentially by a mean field picture that hints about the large K limit. The same game that we played here for this model can be played with other models, which are more interesting from the point of view of computational combinatorial optimization, okay, like K-SAT, XOR-SAT, whatever you have in mind. Okay, so the model is the following. It's a spin glass model with the plus minus j. Let's say it will be 1 in the numerics, but you have to imagine plus minus j, chosen with probability 1/2, and transverse field, and the connectivity graph is a regular random graph, which is usually pictured like this, locally looks like a tree, and so on and so forth, but in reality is something like this, okay? So if you look close here, you will see that every point is connected to k plus 1, where k equals 2, so 3 other points, and you know, sometimes there are small loops, most of the time there aren't small loops, and so on and so forth, okay? So in principle, we want to consider both temperature and transverse field, but we want to look really at the zero temperature thing. Okay, so this is the phase diagram, which somehow is to be expected, and actually there are many works on very similar models, and even some work on this same model. So without transverse field, we are talking about the plus or minus j spin glass on the regular random graph, which has a transition which can be found analytically, and I will actually give you a short argument to find this number here, which is j divided by arctangent 1 over square root of k. The important thing to remember for k equals 2 is 1.135. But the important thing to remember is that for k that goes to infinity, this grows like square root of k, okay? So this already tells us that for k equals 2, you do a bunch of quantum Monte-Carlo numerics, you find this gamma critical, and I will show you how we find the gamma critical, which is 1.82 plus or minus 0.02, okay? But the important thing is that if this phase diagram has to scale to something which is similar to this curve, okay, will change with k, but it has to scale something similar to this curve. In the k going to infinity limit, then gamma critical has to scale like j square root of k too, okay? And one of the arguments, one of the things that I will tell you is essentially how to find this square root of k from a quasi-particle picture. One thing that you have to keep in mind is that, gamma critical, when k becomes large, becomes much larger than j, okay? So certainly in a large k limit, trying to find this phase transition by doing perturbation theory around here, this point, is crazy. What you want to do is perturbation theory around infinity. Okay. So this is essentially my main message, is that this phase transition here has much to do with this phase, much more to do with this phase than with this phase. So almost most probably, this phase transition doesn't know anything about the computational difficulty of the problem down here. Not to say that there isn't information on this line about the computational difficulty. There is plenty of it, because the system has to go to the ground state here when we move along gamma. But it's just not in the phase transition. OK. So by the usual arguments in statistical mechanics, when the temperature is different from 0, the Trotter dimension is finite. So if you go to the phase transition is a place where you can do a renormalization group transformations and look at larger length scales. And this means that at a certain point, your Trotter dimension, which is 1 over t, will essentially become irrelevant, and you go back to the classical point. Okay? So it's to be expected that all this line, except this point here, has very similar properties to this point, this transition point here. And the transition can be seen by looking at the spin-spin correlation function. The connected correlation function, as usual, is the derivative of the average of the spin with respect to a field at the point I, with respect to a field put on the point j. Okay? And typically, this correlation function decreases exponentially with the distance. Okay? At the critical point, this correlation length usually diverges. And why does it diverge? So this is a little bit for experts. On the regular random graph, which locally looks like a tree, this computation, this derivative can be just expanded by taking derivatives of what are called cavity fields. And all these things are essentially almost independent random numbers. They're not really independent, but kind of. And so this product generates an exponential factor. In particular, in the paramagnetic phase, this derivative explicitly is this thing here, which has hyperbolic tangent, 1 over cosh, 1 minus hyperbolic tangent square, and blah, blah, blah. But when you are in the paramagnetic region, these fields H are actually going to 0. When you send them to 0, this thing goes to 1, this goes to 0, so this thing just becomes hyperbolic tangent of beta j. Okay? I'm talking about the phase transition at finite temperature here. But on a regular random graph, so good. So this looks like there is a product of things which are less than 1, so this should decay exponentially. So how can you have a transition? Well, the transition is due to the following thing. On a regular random graph, you take 2 random vertices, and they typically are at a distance L, which is log n divided by log k. Okay? All couples of vertices are at this distance. And at this distance, it's not true that there is only one path that connects the vertices, but the number of vertices is actually, the number of paths is actually order k to the L. Okay? So you have to sum this susceptibility over all the paths that connect I and j. And since for every path this calculation is correct, this is a random number because j is plus minus j. A minus 1 is plus minus j. So the typical value of this random number will be, take the square root, you take the square root of the number of terms times the typical value of the thing. And you see here now that you can have a transition. And the transition is when this thing actually goes, if this product decreases exponentially with L, which is also n, the system size, then you are still in the paramagnetic phase. Then at a certain point, this doesn't happen anymore. And this gives you a critical temperature. Okay? So on the regular random graph, it's very important that there are many, many paths there. OK. So unfortunately, at t equals 0, we are not able to do this, anything like this. Okay? We don't have analytical control of what happens there. So we resort to what Anderson called the indignity of the numerical computation, which is nothing. It's just its own dignity. And so we did the quantum Montecarlo up to 160 spins. So, and then we went to sufficiently low temperature that we were sure we were in the t equals 0 limit. And we looked at quote-unquote classical quantities, quantities which have a counterpart in the classical system, and quantum quantities, which are like entanglement and this quasi-particle picture that I want to tell you about. And this will lead to discussing the localization of these quasi-particles. But let's begin with a summary of the numerics, which already tells us something. OK, so first of all, the Renyi entropy. So everything, this is a gamma critical. It's extracted from finite size scaling of different quantities, which I will show you separately. So you have a gamma critical, which changes with 1 over n for different things. The Renyi entropy, the correlation length from the mean correlation function, the correlation length from the maximum correlation function, and the order parameter. So you see, they all converge more or less at the same point, which is this estimate here. And the scaling, but the coefficient is actually different. And the thing which is the least sensitive to the finite size effect is the entanglement entropy. The thing which is most sensitive, apparently, to the finite size effect is the order parameter. I'm just saying that this slope is larger than this. Okay. OK. So for example, the Edwards-Anderson order parameter, the raw data looks like this. You go from 40 to here, there is only 140 spins, and they go like this. And then you do finite size scaling, changing, finding a gamma critical, gamma Cn. Here, you don't need to change a QEA. And you find the gamma C of n such that they all go on the same line. And here there is a straight line which says that the critical exponent is 1, which is, by the way, the same critical exponent you find in the classical transition. So this thing doesn't change. Okay. Then you look at the correlation length, at the correlation function between the spin-spin correlation function. And what you find is, now let me explain you what this max means. No, actually, let me explain it right now. So you take a point I and a point J, and you take all the points J at distance R from the point I, okay, of which there are k to the R, and then you take the maximum. Okay? And this is C maximum of R. And this thing is very well fit by a stretched exponential. In fact, here I'm plotting this C maximum versus R over Xi, where Xi is a fitting parameter, and A is the other fitting parameter, and A varies with the disorder. In this particular case, it's about 1/3. Okay. So this falls nicely on a straight line, which means that this law is. And this allows us to get the other fitting parameter, which is the correlation length. The spin-spin correlation length has a maximum at the transition, okay, and decreases with increasing system size, okay, which is quite bizarre. And so both if you take the maximum, if you take the mean over all the points at a given distance, they seem like they're going to the same value, which is about 1 for that fitting 4. Then how did we get the Renyi entropy? The Renyi entropy is gotten by doing quantum Montecarlo on 2 replicas and taking the difference of the free energies of the 2 replicas coupled on the part of the system that we are tracing away or decoupled. I'm not going into the details of how this thing is done. We can discuss later on if you want. But it's done. And what you get is these curves here. So you increase the system size from 10 to 100 in this figure. And you see that typically the entropy grows linearly with n everywhere. Okay? And it has a peak which shifts to the right, but quickly asymptotes around 1.8. Then you do finite size scaling, and you find that they fall on top of each other quite nicely, except the point here. But this is, we know from other studies, for example, in problems of many-body localization, that the entanglement entropy at the transition typically have very large variance, sample by sample variance. Okay, so this was to be expected. Okay. So, all right. Now let's go to perturbation theory, the thing that I told you before. Okay. So we found that the transition point is gamma is equal 1.82. And let's assume that 1.82 is a large number. Okay? It's certainly larger, more a large number than a small number, but you know, you need a little bit of fantasy to. Okay, so we think of these as a perturbation on these, right? And therefore, we look at the eigenstates of H0, which are very easily written down. It's, say, all the spins aligned along the plus direction is the ground state as energy minus n times gamma. Then there are the n-degenerate states in which I have a spin flip along I, which is degenerate and has energy E0 plus 2 gamma. And then 2 spin flips, E0 plus 4 gamma, and so on and so forth. And then we think of the minus x spins as particles. Okay? So sigma zi, sigma zj flips the x spin, right? So it can do 3 things. If it acts on a site where there is nothing, it can create a couple. Okay? And this costs energy 2 gamma. If it hits a site where there is a couple, it can annihilate it, and this costs energy minus 2 gamma. Okay. If it hits a site where there is a particle and on the other side there is no particle, it moves the particle from here to there, and this costs no energy. Okay? So at the lowest order in perturbation theory, I can forget about these two, the first 2 things, and just consider the last one. So I have to do degenerate perturbation theory on these graphs. And essentially, this means that I have to diagonalize the matrix J minus Jij, okay, which is a sparse matrix with plus or minus 1. And this is a well-known problem. The result is that there is a band which spreads out, okay, with slope minus 2 square root of kj. And the single particle sector would intersect the ground state at gamma critical when this thing becomes 0. Okay? So when this thing becomes 0, and this is gamma critical square root of kj. Now let me remind you that square root of 2 is 1.4, which is quite close to 1.8. Still, again, with a little bit of imagination. Okay, this is the way you solve the problem if you're interested. Since I have 10 minutes, I can probably talk about it. So the spectrum of this matrix here is almost, so you can solve it like this. You can write cavity equations for the propagator. And this gives an equation for the propagator for the z. Z is the real, the energy plus the small part, a small imaginary part. And so since jij squared is equal to j squared, then this is a deterministic equation you can solve. You get this thing here, and you get semicircle law. So the density of state of this Hamiltonian here is a semicircle law, which ends at 2 square root of k times j. Okay. Now you would say, well, but then this is the same as the ferromagnet problem, right? Because if I have a ferromagnet, if I have all the j's equal to, all the j is equal to plus j, then this will be the same, right? This will be the same equation, then I would solve it, they will find. But there is one thing which is different. If all the j's have the same sign, then this is a Perron-Frobenius Hamiltonian, and there is an extra isolated eigenvalue at minus jk plus 1. And this dominates the physics of the ferromagnet, and doesn't dominate the physics of the spin glass. So if you go to two particles and you assume that they don't interact because you neglected the terms that make them interact, then you start from 4k, but then the slope is twice as much, right? So in the non-interacting many particle sectors, all the ground states of all the sectors intersect the ground state at the same point, okay? Which is, as I said, a square root of k times j. Oh, by the way, this is an exact diagonalization of a system with 10 spins. And the color is the average of sigma x, which is the number of particles. And so you can see that this looks like this, except that then they start interacting here. So let's try to put back some of the things that we have taken out, and let's see at least what's the feeling, what's happening. So, OK, so we said that we had a couple, we act with sigma z, and this disappears. OK, so there is the amplitude per unit time is minus j for this event to occur, and the energy change is minus 4 gamma. Okay? I can mimic this thing if I only consider 2 particle processes, not 3 particle processes. If I can mimic this thing by saying that these 2 particles, if they are on top of each other, they attract with an energy minus 2 gamma. The 2 here is because there are 2 processes possible. This can jump over here, and this can jump over here. So there must be a mismatch of 2 in order to get the same amplitudes for the ratios. So to order rho density of particles, I can substitute, I can consider these particles as just having a point-like interaction, which is attractive, okay? And if I do this in mean field, the energy of the ground state gets corrected by minus 2 gamma times rho. Now, if I solve this equation as a function of gamma again, I get the correction, which is plus rho. Okay? And then there is a correction which is of order rho squared, but this is of the same order of the things which I have neglected, which are 3 particle things. So the shift is in the right direction. It's towards larger gamma. And the biggest change occurs for states who have more quasiparticles. OK, so my point is that in order to understand the transition, we need to understand what happens to these quasiparticles when there is interaction. Okay? And so this leads to a lot of questions which we have not answered in the paper, but which we have put forward and we are working on. So the phase transition is governed by the dynamics of the quasiparticle, okay? In particular for large K. And then you can ask, what's the nature of these quasiparticles? For example, are they localized? Okay. In the non-interacting approximation, no, because we know that the eigenstates of the sparse matrix Jij, they are all delocalized. Okay. But we also know that if you want to see the transition, you have to go at finite density. At finite density, the particles interact with each other. And there have been several works put forward in the last years in the context of many-body localization. One is by Boris and Lev Yoffe, and there is also some paper by Michael Fisher, I think. There is some paper by Markus Müller about localization of highly excited states without disorder. Okay? So interaction and graph disorder, but even without graph disorder, this could lead to localization. Is it some kind of many-body localization? Does the localization of quasi-particle lead to exponentially small gaps? Because we know that many-body localization tends to give exponentially small gaps because the eigenstates tend to be very different from each other. So what happens when the couplings J gets increased? For now, in the opposite limit, gamma much less than J, the quasi-particle picture gives room to the Z-spin picture. Okay? Now, gamma is the perturbation. Does this transition have to pass necessarily through a localization transition? Okay. So this is the paramagnetic phase for small j. This is the spin glass phase for large j. And here it's non-interacting particles. Then particle interaction becomes important. Then you have this transition that I told you, which is the spin glass transition. And then maybe there are localized particles here because they are all crammed together. There's a large density, and they interact strongly with each other. And so this should come with a question mark. And OK, so this is the conclusion. So let me repeat what I said. We looked at the properties of the quantum phase transition, quantum Montecarlo to get correlation function, entanglement, entropy, et cetera. And we looked at the properties of the phase transition from the quantum, coming from the quantum paramagnetic states. And this actually, I think, gives a better picture of the transition. Things to do, we could play the same game in other models, K-sat, XOR-sat, and so on and so forth. For example, studying the one particle approximation, two particle, and so on and so forth. And then we need to understand what's the physics of these quasi-particles and what is the relation with the scaling of the gap at the transition and within the spin glass phase. Yeah, and then let me flash this thing. Just to, if you don't know, we are having a conference, very similar topic, actually, on the same topic. And also, we are going to talk about quantum simulation at ICTP on the 22nd, 26th of August, 2016. OK.
Hi, Anto. I'd like to ask about the algorithmic implications of your discoveries, because the problem you're looking at is computationally interesting, finding its ground state.
Yes.
So, you talk about other problems, but this problem is already computationally interesting.
Yeah.
So if you decrease the field, you first seem to be going through a phase transition where the gap might be polynomial.
Yes.
And so that looks like good news for the adiabatic algorithm. So then do you expect that as you go further down, that you're going to encounter, let's say, the kind of perturbative crosses that Boris focused on, or other obstacles to the success of the algorithm? So
this is exactly this thing that I put here, right? So you come from large gamma, small j, large gamma, okay? And then you come down, you do your adiabatic algorithm coming down like this, and then you encounter this transition where the gap is polynomially small, and it's due to the fact that the kinetic energy gain of the band of these quasi-particles beats the ground state, okay? But then these quasi-particles also determine the structure of the excited states. And so if they are localized inside the glassy phase, then you get exponentially small gap, okay? So I still don't have an answer to whether this quasi-particle picture leads necessarily to an exponentially small gap inside the phase, but we are going to explore this.
So I'm a little bit confused by the fact that at finite temperature you are looking, so the trajectories that were large of the size of of the system size were important to determine the transition. So you had this exponential number of paths and so on. So the loops were important, but here at 0 temperature you are looking at short trajectories where the system is well approximated by a Bethe lattice, by a graph. So why?
No, I'm not looking at small portions of the regular random graph. You really have to look at the spectrum of the full regular random graph, even for this quasi-particle picture. So is this what you mean by trajectories?
So this analysis is like for Bethe lattice, right?
No. I mean, this one is not for, which one is for, what do you mean for Bethe lattice? This one? Yes. This one? Oh, this happens to work also for the regular random graph. Okay. So it's something which has to do with the fact that we are looking at the density of state. If you want to look at other things which are more complicated, like correlators, then there is a difference between Bethe lattice and regular random graph. But for this particular thing, there isn't. If you do the numerics on the regular random graph, up to 1 million sites for diagonalizing Jij, you get this thing.
Other questions? Okay, let's thank Antonello again.